Hi, my name is Giacomo, and I will give you an overview of some data science related projects at IBM Research. And I'm going to start with just a little bit of background on myself, and then I will talk about some of the intersections between optimization and machine learning that I've been looking at in my research, and also some of the intersections of optimization with quantum algorithm, which is another huge part of my research. Um, so just a few things about myself to set the context. I'm working as a research staff member at IBM TJ Watson, which is a research center located in New York State, and I'm working in the quantum algorithm group. Um, Before moving to the quantum algorithms group, I was in the mathematical sciences and business analytics group. I actually did part of my studies in Italy at the University of Florence, where I have up to a master's degree in computer engineering, Ingegneria Informatica. And then I moved to École Polytechnique in France for a PhD in computer science. I then worked as a postdoctoral research fellow at Carnegie Mellon University and at MIT, and finally worked for a few years as an assistant professor at the Singapore University of Technology and Design, after which I moved to IBM TJ Watson. And now one may ask, what is the common theme about all these places where I've been and where I worked? And the answer is very simple. I've been working on optimization. Many flavors of optimization, but still always optimization. So for you, I'm assuming that the most interesting part to hear from me is what am I doing at IBM Research? And so I can give you a very brief overview, and it will be brief because IBM Research does many things. Um, in general, IBM Research does a mix of applied and foundational research. So some groups tend to work more on applied research, some groups more on foundational. Generally, I've always been in groups that work on more foundational research, but groups collaborate together very often. So there are always many opportunities to work on different projects. And some of these projects come from other IBM divisions. Other times they come from industrial partners or clients or even government entities. And when it comes to the research, some of the output produced is made available in the public domain. And by this, I mean that sometimes the output of the research is published in journals or any other suitable outlet for publication. And sometimes if you produce software, it is made open source. But of course, this is not always the case. So some of the research output may be kept confidential, especially if it's part of collaborations with other companies. Now, of course, this is a very general overview. It is very hard to characterize what happens in all of IBM research. I can only give you an overview of what I see and what I have done. And in my specific case, I spend most of my time working with colleagues to determine what problems are relevant to solve and then trying to solve them. And most of the time, what I do eventually gets published. Sometimes it also gets patented, but I would say in the vast majority of cases, we do produce publications that are then in the open domain. And of course, the crucial question here is what are relevant problems? And here there is interest in both foundational research questions that may lead to important discoveries or things which are of more direct industrial interest. On top of that, I also collaborate with industrial partners and clients, and I also write software. I will talk a little bit about some of the software that I write in just a few minutes. Now, I don't want to bore you too much with just talking about myself, so I will jump straight into some of the things that I have been working on while at IBM Research. And you'll see that all of these are related to optimization in one way or another. And I'll start with a couple of things that are at the intersection of optimization and machine learning. So for some time, I worked with several other colleagues on some ideas to translate symbolic regression into an optimization problem. So what is symbolic regression? In machine learning, one of the common tasks is to build a model that explains a data set. So you have some data that you would like to construct some form of model that is able to accurately predict different unseen data points that come from the same distribution. In symbolic regression, you do share this task, so you are trying to find a model that explains some data set, but you don't assume that the functional form of this model is known a priori. So generally, if you construct, for example, a neural network or some support vector machines, the output of training a model will be some model that belongs to the class of all support vector machines, all of which, for example, or neural networks, all of which have some pre-specified functional form. And in symbolic regression, you just want to find a mathematical expression, whatever that is. So the space of the outputs of learning a symbolic regression model is the space of all possible mathematical formulas. So in particular, to perform symbolic regression, we need to define a space of valid mathematical expressions and a mechanism to explore this space. Now, in this specific piece of work, we decided to represent mathematical expressions by means of expression trees. And you can see an example of expression trees on the slides. So what you can see here is that if I have an expression 2w1 plus w2 to the third power plus 1, I can represent it as a tree where I have some leaves that represent my variables, w1 and w2. And these two variables get added together because there's a plus between them, after which I take the power of this whole subtree expression, and the exponent of the power is 3, and so on and so forth. So this is a convenient graphical way of representing any mathematical expression. And so what we did is that we formulated an optimization problem that takes as input a data set. So the data set as usual consists of several tuples where you have some variable that you have to explain why, and a bunch of independent variables, x1, x2, up to xn. And the goal of this optimization problem is to construct the smallest formula of x1, x2, up to xn that produces y. And here, when I say smallest formula, I mean any valid mathematical expression. So in order to do so, what we do is that we translate all the valid expression trees as the search space of an optimization problem. And then we optimize over this search space. So in particular, the decision variables of the optimization problem that we define determine an expression tree. So the structure of the tree and what are the leaves of the tree, what is assigned to each one of the nodes. And to give you an example of what this type of approach is able to produce, here I'm reporting some results from using a data set taken from NASA that has several tuples. This is data actually recorded from NASA, and it contains information on planets and stars. In particular, we have, for each planet, we have the corresponding star, and then we have the orbital period of the planet, the mass of the star, the mass of the planet, and the major semi-axis of the orbit of the planet. This is real data. And And then we use the approach that I just described to try to explain the the major semi-axis of the orbit D. So we try to find a formula where the 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 dependent variable is D. So D is our Y here that we want to find. And by running this approach, we're actually able to find simplified expressions of Kepler's third law. Um, Now, Kepler's third law would be that d is equal to the third root of some constant times tau squared times capital M plus small m. And we're actually never able to pick up the dependency on the small m because this is the mass of the planet, which is tiny compared to the mass of the star. So even when we require very small error in the formula, we find an expression that is accurate except for this for the dependency on the mass of the planet. And here what you can see in this table are the formulas produced by this optimization approach on different data sets, all of which are taken by taking subsets of this NASA data set and imposing different bounds on the maximum relative error that the formula can produce. So if we require only 2% relative error, we find, as I said, this quite accurate expression for Kepler's third law. And then as we increase the allowed relative error, we found formulas which start getting simpler and simpler. For example, if we allow very large maximum relative error, then this approach tells us that a formula that just looks at the square root of tau is actually a good answer. And of course, if you want to get smaller error, you need to increase the complexity of the formula that is allowed to be returned by the algorithm. So this is one of the examples that I wanted to show you. It's very much at the intersection of optimization and data science. It's not the only example that I have where we look at the intersection between optimization and machine learning. There's a second one, and this is related to what is generally called hyperparameter optimization. And the context for hyperparameter optimization is the following. It's the context of trying to automatically deploy a machine learning model. This is, of course, something that is very valuable because machine learning is used extensively in many fields of business, and therefore there's a lot of machine learning models that gets constantly produced. And finding ways to automate this process is, of course, something that can be a game changer and can save a lot of time. Now, one thing to note is that every machine learning model has a lot of what is generally called hyperparameters. So what are these hyperparameters? If you take a machine learning model, for example, a support vector machine or a neural network or random forests, you will see that before you actually train one of these models on a data set, you have to choose a number of parameters. For example, for support vector machines, you need to choose the type of kernel that is used in the support vector machine. You need to choose some regularization parameter and so on and so forth. And if you're trying to train a neural network, then you need to decide the architecture of the network. You need to pick activation function for the layers of the network. You need to choose a learning rate and so on and so forth. So for every machine learning model, there are several parameters, which we will call hyperparameters, that you need to choose before you actually start the learning phase. And then after you choose the hyperparameters, you can train your model and then look at how this performs. So if we want to look at the problem of choosing hyperparameters as an optimization problem, we can formulate it as follows. So suppose we're given some data set, And then for some given value of the hyperparameters of a machine learning model, whatever these hyperparameters are. For example, for the neural network, there will be something that determines the architecture, the activation functions, and so on and so forth. So as I was saying, once we're given a data set and a set of hyperparameters for a model, then we can define some function, which is what we call here Fm of the data set and the hyperparameters, as the performance of the machine learning model M on the data set. And here you can think of your favorite measure of performance, something that estimates the generalization error of the model. And then what we do is that we try to optimize the value of these hyperparameters x1, x2, up to xn that optimize this measure of performance. And notice here that I'm not telling you what is the form of this function f, because in fact we don't really know what is the form of this function, but we can certainly assume that this function exists. Because once the dataset and the hyperparameters and the machine learning model are given, then I can compute the value of this function. So putting everything together in this optimization perspective, our goal is to search for the values of the hyperparameters that optimize the measure of performance of a machine learning model on a specific dataset. And there are several important things to note here. One is that we do not know the form of this function. As I just said, this function is something that we can evaluate, but we don't have a mathematical expression for it. What we know is that given D, given the type of machine learning model and given the hyperparameters, we have a way, we have a procedure to compute the value of f. However, not only we don't have an expression for f, but it is in general a stochastic function. So what I mean is that the output of this it should be considered a random variable. If we train the same machine learning model with the same hyperparameters, on the same data set, we may obtain different values depending on a random seed. So there is stochasticity involved in evaluating this function that determines the performance of a model. And on top of this, even simply evaluating this function may take a very long time. If you think about training a neural network, this could take minutes, it could take hours, it could even take days. So whenever we try to optimize this function, clearly we should try to optimize it while evaluating it at a small number of points, because every time we want to evaluate this function at some point, it may take a lot of time. And another source of difficulty is the fact that these hyperparameters that we need to choose may be continuous values, so real numbers, but they may also be discrete values like integer numbers. If I'm deciding how many units I want to put in a layer of a neural network, that's an integer number. I cannot put 3.5 neurons. But they can also be categorical variables. So here, by categorical variables, I mean variables that take value in some finite set that doesn't have a concept of order. For example, if I choose the type of the kernel for a support vector machine, I can use a polynomial kernel of some degree. I can use a Gaussian kernel, and I cannot compare a polynomial kernel to a Gaussian kernel. I just know that they are different, but there is no notion of distance between the value polynomial or the value Gaussian for the kernel. And similarly, if I look at the activation function for neural network, I know that there are several values that are possible, but among these values, I cannot really compare them. I just know that they are different, and then I need to choose one of them. Whereas if we're talking about the example that I was given for the number of units in a layer of the neural network, so what I call discrete parameters, these values, they're numbers, so I can at least compare and know which one is larger. So all of these things, they add to the difficulty of the problem. And And so part of my work at IBM involves working on algorithms and software to solve this hyperparameter optimization problem. Um, and in particular, I work on a library that's called RBFOpt, and this uses techniques from an area of optimization that is called derivative-free optimization. The specific approach that is implemented in RBFOpt uses the idea of a surrogate model of the objective function. So what's a surrogate model? It's a model that we try to learn to match the shape of this objective function, this function fm here, that we don't know. So we evaluate the function at several points, and then we try to guess a model for this function, and then in an iterative fashion, we try to improve the model, but at the same time, we also try to find better points based on the knowledge that we acquired of this unknown function. So this is sort of the general scheme, but of course, as you might imagine, there are several tricks that are involved in trying to make this general scheme work. In particular, RBFOpt uses many tricks such as local search. It does automatic surrogate model selection by looking at the performance of several models for the unknown objective function. It uses many techniques to rescale the function value so that we don't run into numerical troubles or ill-conditioned systems and things like that. And just to give you some visual example of what applying advanced optimization techniques can do in terms of savings, I'm going to show you here the performance of just a few different optimization algorithms on a problem of this form. Here I'm using an artificial function that we're trying to minimize, and this function is given to some optimization algorithms as an oracle. Here by oracle, I mean that these algorithms are only able to evaluate this function. They do not know the form, the mathematical expression for this function. They do not know the gradient of this function, but they're allowed to evaluate this function at any point. And because, as I mentioned earlier, in typical applications, each of these function evaluations can take a very, very long time, we put a limit on the number of function evaluations that each algorithm is allowed to do. So in particular here, most algorithms will work with only 50 function evaluations allowed. So we tell the algorithm, you are only allowed to evaluate this function at 50 different points. Try to find a minimum of this function. And in this example, the minimum is actually located here in this part of the domain. There's actually another minimum right here. So this first example is showing you the points that are evaluated by an evolutionary algorithm. So evolutionary algorithms and genetic algorithms are very often used for this type of problem, but they can be inefficient. You can see in this case, the algorithm with only 50 function evaluations does not actually find a point close to either of the global minima, which would be here or here. We can then increase the number of points that the algorithm is allowed to evaluate. This is the same algorithm, but now it is allowed to evaluate 100 points. It still doesn't really get too close to the optimum. Now, eventually, if we allow 1,000 points, then the algorithm does find something which is very, very close to the global optimum. And then you can see this funny distribution of points here, which is most likely due to the algorithm mutating the best candidate that it found. So this is an example of the performance of an evolutionary algorithm on this specific function. Here's another example. This is the optimization approach called controlled random search, which is a mix of random search and then local search based on the best points found. And you can see once again that with just 50 points allowed, in terms of evaluation, this approach does not get very close to the global optimum. It gets something not too far here, but the true optimum would be closer to the center of this ellipsoid. And the last example is taken from the algorithm implemented in the library that I developed. And you can see that it does a much better job at finding a point very close to the global optimum with even just 50 points. And another interesting thing that you can see is that it distributes the function evaluation in several parts of the domain. And the reason it does that, it's because it is trying to learn the shape of this unknown function. And then, as you might imagine, after learning the shape of the function, then it has a much easier time to in trying to guess where the optimum of this function might be. And so to conclude this part, as part of what I do at IBM, I also develop software, but of course also the algorithms that are implemented in the software. And this is very much, once again, at the intersection of optimization and data science, in particular machine learning. And the last part of what I would like to talk about is about quantum algorithms. This is a huge part of my research in the last few years. And this is something that you may have heard about, you may not know much about. I think it is extremely interesting because quantum computers offer a different model of computation. And if you're not familiar, the idea of a quantum computer was proposed in the 80s by Feynman. And these were initially thought to be devices that could be used to simulate quantum mechanics, so to simulate nature. And then, as it turns out, they also have other applications. And since this visionary idea, there has been a lot of progress in actually constructing quantum computers, so much that now you can use real quantum computers on the cloud. So you can design your quantum programs and run them on the cloud and get results. And I should not hide the fact that even though there has been a lot of progress, still a lot more progress is needed if we want to perfect the technology. So the current hardware implementation of quantum computers are still very noisy, and they still have several difficulties that should be dealt with if you want to construct a computer that behaves like the theory predicts. So why are we even interested in this? Well, as I said, the main reason is the fact that quantum computers use a different model of computation from traditional computers. We are used to computers as machines that are based on a model that in theory is called the Turing machine. And we have at this point, intuitive understanding of what they do. Quantum computers use the laws of quantum mechanics to perform their operations. And for this reason, there are problems that can be solved faster on a quantum computer than you can do on a classical, by classical here I mean not quantum computer. And I should emphasize, this does not mean that you can solve all problems faster, but there are some problems for which it's been shown that quantum computers are faster than a classical computer can ever be. And in particular, Turing machines can simulate a quantum computer, but it's not known if they can do so efficiently. And so what this means is it means that there are still some tasks. One famous example is integer factorization, that it's not known if they can be performed efficiently on classical computers, what we're used to, but it's known that they can be performed efficiently on a quantum computer. And this motivates us to study what are the possibilities and the limitations of quantum algorithms. So in particular, as you might imagine, I'm interested in algorithms, quantum algorithms for optimization. So a large part of my time is devoted to trying to find quantum optimization algorithms that are more efficient than their classical counterpart. And so to do this, there are mainly two strategies. And one strategy is to try to quantize. Here, quantize means to make quantum some existing optimization algorithm. But alternatively, one can try to design new algorithms that are really based on quantum mechanical ideas that don't have a classical counterpart. And I should note here that even though I'm really focusing on optimization, the same is true for other areas of data science. In particular, there is a lot of interest in quantum machine learning algorithms. And many of these areas are still very new, so there are still very basic discoveries that are being made. Now, when it comes to quantum optimization algorithms, some well-known classical optimization algorithms have in fact been quantized. There has been work on interior point methods, on the multiplicative weights update method, even on the simplex method, and this is something that I devote a lot of my time to. But as you might imagine, this is a very new and very exciting area, and so making progress is something that often turns out to be very difficult. At the same time, it's clear that this potentially has a huge impact on the theory, but also the practice of data science. And and for this reason, I'm extremely excited, and this is where I spend most of my time in trying to understand possibilities and limitations of quantum algorithms for a variety of tasks, specifically optimization, but in general other tasks that come from data science and in an industrial environment. And I think this is all that I wanted to tell you. Thank you very much for listening, and enjoy your data science.